cannot. Think it's okay, right? Think it's okay. Nonlinear one. Okay. Thank you very much, Boyan. So this is the third and last lecture. I'm still surprised someone survived. So I'll try. So this is my last opportunity to kill the audience. And I'll try to do my best. Okay, the last things I've been talking about are linear and nonlinear potential estimates, pointwise estimates for solutions to these problems. Right, we should switch on the lights, right? Can you switch on the lights? The first row of the lights. You switch on, yeah, okay. But you are not able to read the, no, not really, okay. No problem. Okay, now it's okay. So I will consider general quasi-linear equations of this type, whose model type for p larger than 2 is given by the p-Laplacian operator. But as I stressed the last time, the real point in this estimate is really passing from the linear to the nonlinear case. Because in the linear case, you have explicit representation formulas via fundamental solutions, and they allow to give pointwise estimates immediately via potentials. In the nonlinear case, you do not have these formulas, and therefore you have to take another path. So let me summarize the results of the last time. So the first result is a pointwise estimate for U for solutions to the p-Laplacian operator, and this is due to Kilpeläinen and Mali, and this tells that you can pointwise bound U by the Riesz potential plus a power plus the usual localization term. Of course, the thing you have to retain here is the first one, because the other one is just a constant, is a localization term, and it has nothing to do with the real pointwise behavior. Okay, it has to do with an interplay, but when R go for a fixed R, this is really the leading point. Okay, and this is due to Kilpeläinen and Mali. So the first, and this is optimal. So as I told you, a first step towards the gradient theory, let me remind you, of course, the W1P for P equals to 2 coincides with the Riesz potential, and therefore you have the usual estimates via the Riesz potential. So you catch up again the usual estimate. So a first step towards a gradient estimate, a gradient potential estimate, has been given, and this is suboptimal, and is the following one. It's slightly suboptimal. This is Actamat, I think 94, plus this guy. And this was the first result in this direction. After the case, for the case p equals to 2, okay, for the case p equals to 2, this is due to myself, and this is in GEMS 19, otherwise it's due to Dutzer and myself, and it's in the American Journal of Math, same year. Of course, there was a delay in publication. This is still suboptimal, and the real twist, okay, let me recall you that I'm just considering the case for simplicity, p larger or equal than 2. And the real twist was finally achieved with Tuomo Kuusi. And this is a real surprising result because it tells that essentially there's no difference between the p Laplacian or any quasi-linear possibly degenerate operator and the Poisson equation, because you can pointwise bound this guy via I1 of mu xr plus du. That's what you can do. And this is a really, this is a result that actually, in some sense, trivializes the theory, because it tells that any result you want to have on the gradient can be now obtained by just looking at the potential, and there is potential exactly as for the Laplacian. Of course, in the Laplacian case, you do not see this power, which is due to the scaling. And in fact, for p equals to 2, this is purely 1. But otherwise, you have the purely Poisson equation theory also for any quasi-linear degenerate equation. And also continuity results can be obtained in terms of potentials. And this is a result by Tuomo Kuusi from Helsinki and myself. This is on archive this year. An announcement appears in the Compte Rendu Mathématique maybe 2011. Okay, now the point is that this estimate tells you everything. In particular, when mu is equal to 0, you see immediately that this term disappears, and you go back to the classical L infinity L1 reverse estimate, which is natural for solutions. So in particular, you go back to the usual pointwise estimate. Now, our first question is the following one. What happens if you do consider more general operators of these types, and now, according to the classical De Giorgi, Lagrangian, and Altseva theory, you want to prescribe a measurable dependence on the coefficients. So this is measurable. And obviously, a model case is given by just adding an elliptic coefficient to the p Laplacian. This is a classical model case, and this guy is bounded from below and from above, bounded away from 0 and infinity. Okay, of course, you wonder if this estimate still holds, and the answer is, of course, not. Because already in the best possible case, you know that the gradient is not bounded. If this estimate would hold, you would know that the gradient would be bounded when you have measurable coefficients, and this is in general false. So in order to understand what kind of estimates you can get, you just look at the best possible case, and of course, you have to cook up an estimate that in the best possible case gives just what you have when the right-hand side is very good. So, okay, of course, the best possible case is when the right-hand side is equal to 0. So therefore, let me recall the maximal gradient regularity for equations of this type. Remember that we are considering functions that lie in the Sobolev space W1P, locally at least. And therefore, the maximal regularity is given by the so-called Gering's lemma. So this is Gering's lemma that tells you that there exists a delta, universal delta, which is independent of the solution, which is only dependent by p, by the ellipticity coefficients of the operator A, but is otherwise independent of the solution, both of the solution and of the equation, such that U belongs to W1P plus delta. This is a very fundamental result that in the linear case was first discovered by Meyers. In fact, it's very often called Meyers estimate, and the modern proofs for nonlinear operators are based on the use of the so-called Gering's lemma that was first initially developed in the context of quasi-regular mappings. So actually, and therefore, okay, this delta is quantifiable, but it's open, in the sense that you never reach a precise delta. This is a classical open-ended condition, and this very often happens when you have self-improving properties. In some sense, you get a maximal QM such that U belongs to W1Q for every Q less than Qm. That's what you really have, maximal. Okay, therefore, it is clear that if you want to have a gradient estimate, you cannot go beyond this maximal regularity case. So what you can have, you have, of course, say bye-bye to the pointwise estimates, because pointwise estimates, they immediately give you the L infinity. And you have to look for an analog that just involves level sets of the gradients. And the theorem, which is actually an ancestors of this theorem, because I wrote this theorem much earlier. So I first wrote this theorem, and then we understood that it was possible to go to the pointwise gradient estimates. And this is published, this is a paper published in Mathematische Annalen in 2010, and tells you the following thing. So first of all, in order to measure the integrability of the gradient, you go for the maximal operator, for the standard maximal operator. So you fix a ball, and then you consider the so-called restricted maximal operator of a function. That's the sup of all possible averages of y and B row contains the point x and is contained in a capital R. So this is the localized, let's say, the restricted maximal operator. It's just the usual uncentered R-delittle operator. So it's uncentered because you take the sup of all averages, but they are not necessarily centered at x. And they must be contained in BR. This is just a technical fact. Of course, by the classical, by the very definition of maximal operators, if you want to know the gradient integrability, you can look at the maximal operator because the LP norms are equivalent. So what does this theorem tells you? That you can fix BR. So you can consider the measure of the level set of this maximal operator that we call now, for simplicity, MF. We understand what it is, of the gradient. Larger or equal than A, then T, A lambda. And you want to control the level sets of this guy with the level sets of the risk potential. Actually, you can do something weaker, but since we are just talking about potentials, let me talk about potentials. So you would like to control this guy with a measure of the level sets of the risk potential. This is observe a local estimate because we are localizing everything to a fixed wall BR. And therefore, this is one U1. You put X here. Let's put R and square R just to be a bit larger, but this is not very important. And of course, you see you can rewrite this estimate in another way, of course. You can plug out this guy here just to respect the scaling. And of course, here you want to see 1 over p minus 1. And then you have this estimate, provided lambda is larger than a fixed constant, then I'm going to specify the initial average of the U, 1 over p minus 1. Question, can you really have this estimate? Of course not. Because if once again you assume that I1 is bounded, for instance, when mu is equal to 0, you would have that this guy is bounded. Because you just take a level set lambda. Oh, sorry, this is larger or equal than lambda. This is larger or equal than lambda. Can you really have? Of course not, because if you take lambda larger than this lambda 0, and then this guy is 0, then you immediately see that the gradient will be bounded. And this is in general not true. So this estimate cannot hold. There's a weaker form, so there's a correction term here, and you have to put a correction term here, which is the following guy, p plus delta, and then you put the same level set. You put this guy. So you control the level set of the gradient with the level set of the risk potential plus the level set of the risk potential with this small constant, because now t can be chosen as large as you like. And now the real important thing here is the power here, because this is the precise form of the estimate that tells you that you can really control, it's a sort of good lambda inequality, that you can precisely control the level set of the gradient with the level set of the risk potential up to the kind of regularity that is allowed by the maximal regularity of the homogeneous equation. Let's see why. Okay, you know, for instance, let's derive a priori estimates. Let's derive a priori estimates. Let me show you how to derive a priori estimates. And let me show you how such an estimate gives you everything up to the maximal regularity. So for instance, we want to know that the gradient is in a certain L gamma, provided I1 mu 1 to the p minus 1 is in a certain L gamma. This is obviously implied by the best possible estimate, which is written here, you see. Now let's see how this is implied by this estimate up to the gamma you can really reach, that is p plus delta. So for every gamma less than p plus delta. Of course, you might wonder what happens when this is equal to this guy. There's no problem because this is an open-ended condition. You can always enlarge a bit more. Okay. Now, you want to provide an a priori estimate for the norm of this guy. And therefore, you can immediately see that you can immediately prove this. And there's no problem because this guy controls the gradient, level sets of the gradient. Okay, therefore, let's multiply everything by what? So you want to get the L gamma norm, so let's multiply everything to lambda to the gamma minus 1, and let's integrate up to plus infinity. So this guy is T, A. A is a universal constant depending only on the problem, while T is still to be chosen. And here, there will be exactly P plus delta. Okay, let's multiply everything by T, A, lambda to the gamma minus 1 and integrate. So this is T, A, gamma, minus 1, and then you take the level set. Okay, this tells you that this is less than or equal than T, A, lambda to the gamma minus 1 times T minus P plus delta, still integral of the level set, plus, okay, big constant depending on T, level set of I1. And now we want to integrate up to plus infinity. Therefore, here we integrate by dA t lambda up to plus infinity. Here, what do? We multiply, we are integrating with respect to d a t lambda. Therefore, you get an a t lambda spared here. And therefore, you get d lambda, and you can integrate. And therefore, you get integral up to plus infinity in d lambda for a big constant depending on t. And now you immediately see that t, okay, let's make the right operations. This t, one t cancels this guy, so it disappears from here. We reabsorb A is a universal constant, so it's not important. We put a constant outside. And what do we have? We have, this is t to the gamma, lambda to the minus 1. And now if you compute this guy, what is this guy? This guy is t lambda minus p plus delta times gamma minus 1 level sets of the gradient in d lambda. This is exactly this guy. If you make the right computation, you have this guy. Now, if you rewrite the estimate, you get at the end, if you rewrite the estimate, what do you get? If you rewrite the estimate upstairs, what is this guy? This is the integral of m of du to the gamma. Less than or equal a constant, which is universal, t to the gamma minus p plus delta. M du gamma. Plus universal constant I1 mu to the gamma over p minus 1. And now to get an a priori estimate, you want to reabsorb this guy into this guy. When can you do? Well, this constant is strictly less than 1. And now you can choose t large enough in order to this guy to be very small. When can you get it? Of course, when gamma is less than p plus delta. So therefore, this theorem allows you to control the level sets of the gradient with the level sets of the I1, provided you are far from the maximal regularity. That is, this theorem is giving you everything you can get up to the point you cannot get anything anymore. So therefore, you can control the level sets of the gradient with the level sets of the potential, paying a price, and this price is negligible as long as you are far from the maximal regularity. Let's say as long as you are far from the forbidden zone. Therefore, integration tells you that this you can reabsorb provided the L gamma norm is not large enough. So this is let's say, the measurable counterpart of this result. Okay, now let me go to the so-called universal potential estimates. The universal potential estimates are something that have been developed by Tuomo Cusi and myself in a recent paper. And they stem from the following observation. These potential estimates are giving you size bounds, in the sense that you want to know how large is u, how large is the gradient. So what about the oscillations of u? So in other words, what about the regularity theory in the spaces measuring oscillations of functions, so smoothness? And it is possible to give new estimates that in terms of potentials are giving a complete spectrum of the regularity properties of solutions in terms of potentials. In particular, you can go back to the old results. Okay, the idea is very simple. And once again, start from the fundamental solution. And let me restrict to the case n larger or equal than 3 and the Poisson equation. So you have the representation formula via the fundamental solution. And the fundamental solution is, of course, like x minus y to the 2 minus n. Now, the first thing you observe is that is the following basic inequality. You take 3 points, x, y, and psi, and these you can easily bound by the following object. X minus psi, 2 minus n minus alpha, and alpha is now between 0 and 1. Plus y minus psi, 2 minus n minus alpha, x minus y to the alpha. You add and subtract alpha. Therefore, if you use this inequality and you write down ux minus uy here and you use this inequality, the following representation formula for oscillations of u works. So here you have a universal constant. Here you get this guy to the alpha. What do you get here? You get Riesz potential 2 minus alpha mu x plus Riesz potential 2 minus alpha y. So in other words, now you have a representation formulas for the oscillations. In particular, if you want to know when U is Hilbert continuous with exponent alpha, you just prescribe that this potential is bounded, and then you immediately know the thing. Okay, is this true for, is there an analog for this for nonlinear equations? Okay, the answer is yes, and it's this joint work with Tuomo Kuusi. I think it's on 11, it's on Journal of Functional Analysis. And this tells that you can actually provide such estimates in such a way that these two estimates become just borderline cases, very special borderline cases of a family of universal potential estimates aimed at providing information not only on the size of solutions and their gradients, but also on their oscillations. Okay, let me give the first result. And of course, if you want to know what are the best results, okay, we want to have an estimate, a family of estimates that covers, for the case p equals to 2, this case, and for the general case, gives you back the borderline estimates. And here you have to split in more stages, because you see there's a difference in these estimates. The optimal estimate here provides you at the 0 level, so when alpha is equal to 0, Wolff potential, and when alpha is equal to 1, a risk potential. Therefore, if you really want to have a universal family of estimates, you have to produce two families. The first one, which stays bounded when alpha goes to 0, and provides suboptimal information when alpha goes to 1, because you cannot catch the risk potential. And the other one that is optimal when alpha goes to 1, that provides this one. Okay, the first family of estimates interpolates between these two estimates and works as follows. This is a theorem that you can bound ux minus uy by what? Okay, absolute value here. There must be the Wolff potentials here, and here you want to have alpha. So what do you get here? You get W1 minus alpha, P minus 1 over P, mu x, plus W mu 1 minus alpha, P minus 1, P, evaluated at Y. This is R, and this is R. So you have the sum of these two guys, plus, of course, the localization term, which is the usual one. And this is x minus y over r to the alpha. Observe that when alpha is equal to 0, this disappears, and you have W1P. So you get the first estimate. When alpha is equal to 1, you get the second estimate. In between, you have everything in between. So therefore, for instance, if you want to know when the function u is Hilbert continuous with a certain exponent, you just prescribe that the Wolff potential, that the corresponding Wolff potential is bounded, and the result provides you with a thing. When mu is equal to 0, this is the classical estimate. And this estimate holds for any alpha between 0 and 1, and it catches up the borderline cases. Actually, this estimate gives you more. Why it gives you more? Because this provides, in some sense, an estimate on the fractional derivative of solutions. Why? Okay, let me go back to a classical work by Devore and Sharpley from 82. And Devore and Sharpley define the following Calderon spaces, telling the following. V belongs to C alpha Q for alpha between 0 and 1, and Q larger or equal than 1, provided the following is true. You take Vxy, Vx minus Vy, then you want Hilbert continuity here. What do you put here? There must be a function which in the language of, which in the language of modern spaces, Sobolev spaces, in metric measure spaces, plays the role of an upper gradient, such that this holds. And this M is now in LQ. You see, when this is L infinity, when Q is equal to infinity, this is the Hilder continuity. Otherwise, you have intermediate spaces. And these spaces are now comparable by tilting alpha to the usual fractional Sobolev spaces. They are not interpolation spaces, but now you have these spaces. For instance, they are surely comparable to Nikolsky spaces. They are, okay, just another way to be fractionally differentiable. So in other words, you prescribe that the oscillations at level alpha of V are controlled locally by a guy that might locally blow up as an LQ function. This very much reminds you the definition via Gallardo norms of fractional Sobolev spaces. So what is this estimate telling you? In other words, M at this stage plays the role of a fractional derivative of order alpha in LQ of the function V. And what is this estimate telling you? This estimate tells you that in this language that you can bound the derivatives of solutions by these potentials pointwise. Up to localization terms. So in this language, you can find a pointwise estimate of any order with Wolff potentials that shows you that in particular, these two estimates are two particular cases, two borderline cases of a general interpolating family of potential estimates, aimed now at showing you that there's a potential controlling even the oscillations of the function U. In particular, for instance, if you want to know that these guys are in a certain fractional Sobolev spaces, you now look at the potential with respect to the alpha, and you prescribe that these guys in LQ and whatever. Okay, of course, this estimate has the one disadvantage that doesn't catch the optimal estimate. This is the real beef here. And therefore, there's another estimate we cooked up that is bounded to give also the optimal case. You see, I find it particularly favorable, this way of expressing fractional derivatives. Why? Because one problem with fractional derivatives is that they are non-local. So with real derivatives, you can write down the equations, you can differentiate the equations, then derivatives are pointwise objects, you can play algebraically with that. With no local objects, the situation is very much different. Here, with this definition, you just reduce the non-locality to a minimal status. Instead of using 1 point, you just use 2 points. You do not have a double integration. Therefore, if you formulate this result in this way, then you have this very nice advantage. Okay, now we want to cook up an estimate that gives you all possible alpha between 0 and 1, but 0 is now excluded because you want to catch up the second estimate here, the risk potential. And this is a more recent work, which is not contained in that paper I told you before, again by Tuomo Cusi and myself. And this estimate tells you that you can do the following. There's a constant here, and now you can do P minus P alpha minus 1 mu x r plus E P minus alpha P minus 1 y r mu. And this is, of course, 1 to the P minus 1. But now the point is that the constant will blow up exactly with this rate when alpha goes to 0. Because at 0, risk potentials do not play a role anymore for what we have seen, and therefore you have to blow up in a certain range. And this estimate is now true up to this borderline case. This is, again, a theorem by Tuomo Cusi and myself, and this is to appear. And finally, you want to wonder if there's an estimate anyway in terms of purely risk potentials, which is uniform in the whole interval 0, 1, and 0, 1 is now closed, and that can give you information on the regularity of solutions. Okay, in order to do this, and this is particularly interesting in my opinion, you introduce, to measure the regularity of solutions, two forms of maximal operators. The first form of maximal operator is the so-called fractional maximal operator, the restricted one of a function f, which is defined simply as follows. You take the sup, as usual, over all the balls centered at x with radius less than or equal than r. You take the averages over br, but you further smooth it out putting this guy here. So you see, this is a better regularization effect of the maximal operator, because you locally kill the possible blow-up of the solution with this row. And this, dimensionally speaking, is comparable to a Riesz potential or to a Wolf potential, because here it's like n minus alpha. And then the second operator is the fractional sharp maximal operator, which is instead defined as follows. Okay, here it's x at the point x. You take, once again, the sup over all possible balls centered at x. The radius must be smaller or equal than r. And now you take f minus the average on the same ball. You average everything. So this plays the role of a sort of a mean square deviation, because you are measuring locally the oscillations of f, saying that in average, f is not very far from its average. But you now correct it with minus alpha. For alpha equal to 0, this is the classical Pfefferman-Stein operator. And in fact, these operators are important because for instance, what Devore and Sharpley observe, and this is actually their starting point, the starting point of the definition of Calderon spaces, is that you can always find a derivative in this way, putting a constant here, and you put the sharp maximal operator to infinity of Vx plus sharp maximal operator V of y. In other words, this, dimensionally speaking, plays the role of alpha of fractional derivatives of a function f of order alpha. This is a choice. This is always true. Then the right-hand side can be infinite. You don't care, but this is always true. Take a smooth function, and this is always true. So in particular, Calderon spaces are those spaces for which this sharp fractional maximal operator belongs to LQ. And then, of course, once you notice this, in order to formulate the new uniform estimate, you want to use maximal operator for the function. Okay, let's see what's let's say, the final estimate that tells you not only how do you reach the borderline case alpha equals to 1, but the loss of regularity when alpha goes to 0. So let's see it. This estimate is a simple following estimate. Okay, you want to measure the oscillations of the solution of at rate alpha. So you want to give a measure of ux minus uy, x minus y to the alpha. So dimensionally speaking, what do you have to do? You consider the oscillations of u, and then you divide by rho to the alpha. So you want to consider the sharp maximal operator of all the alpha of the solution u at a point x. This locally controls the oscillations at alpha order of u. You see, the homogeneity is immediate. These are the oscillations. These are oscillations dimensionally speaking. Then you divide by x minus y to the alpha. Here you divide by the stream radius. And then covering arguments patch you up in a way that the two things can be comparable. In terms of the gradient, how do you bound this guy? You obviously bound this guy by Poincaré. Because if you have this guy, And this is one of the terms that contributes to the soup, giving you the sharp fractional maximal operator. You can immediately bound this guy in this way, 1 minus alpha average of du. And therefore, this is bounded by the sharp maximal operator of the gradient at a point x. Therefore, on the left-hand side of the estimate, you will also find the sharp, the fractional operator of the gradient, not the sharp one, the fractional. And now, this is on the left-hand side. So this incorporates the radii. What do you find on the right-hand side? You find, essentially, you simply find what you expect to find. The previous risk potential and that's it. In particular, you immediately see that since this estimate holds for alpha between 0 and 1, since you have this estimate for any function v, this estimate implies the previous one. Because now you write down this estimate, you put u here, you just replace the maximal operator, and instead of the maximal operator, what can you find? You find this guy. And the advantage is now that this holds uniformly, also it goes to 0. But let's analyze now what happens when alpha goes to 0. So when alpha goes to 0. When alpha goes to 0, you see that you are losing alpha here. Therefore, when alpha goes to 0, this becomes the what? This becomes what you have, IP. So in particular, this is d mu y over x minus y n minus p to the 1 minus p, and this looks very much as the Wolff potential. And what do you have here? You do not have u, because you cannot have u. You have something slightly weaker than u, which is the sharp maximal operator. So in particular, this doesn't give you an L infinity estimate on u, but gives you a BMO estimate of u. Because when this guy is bounded, this implies that u is in BMO by the very definition. Now, what is the difference? What is the gap between L infinity and BMO? It's a log. So you see, there's a log. This controls the regularity of u up to BMO. Therefore, there's a gap of a log type with respect to the Wolff potential estimate. To the Wolff potential estimate, which is this one, sorry. This is L infinity. The other estimate provides you BMO. And so the difference between L infinity and BMO is typically given by a function which is like this one. So there's a loss of log. Of course, this loss of log is exactly the loss you have, the gain you have on the right-hand side. Because what is the difference? Let's write down this potential. Let's write down this potential. If you write down this potential, then you'll see that this potential is nothing else than mu x rho over rho n minus p d rho over rho, and then you put outside 1 over p minus 1. What is the Wolff potential W1p? The Wolff potential is exactly the same thing, but now this jumps inside. So what is the difference between this guy and this guy? A log. Because this makes you the convergence against the higher measure. So these are two dual estimates. The first estimate tells you that you have L infinity and a stronger potential here. The second estimate tells you that you have a weaker potential, that is I1, IP, that differs from the previous one by a log, and therefore you have a loss of regularity in terms of the same log on the left-hand side, and in fact you have BMO. So these two estimates, they are universal estimates that now allows you to recover the previous estimates via as special cases. And in between, you have all the possible kinds of regularity. So you have given a unified approach to regularity theory of possibly degenerate quasi-linear equations via potentials. So in particular, the starting point was this result. Then we went to the gradients. We discovered the risk potentials. And then we discovered that these were just the two tips of a larger iceberg that allows you to control the regularity of solutions via potentials. Okay, just the last result. Just the last results. How long do I still have? 10 minutes. Okay, the last result before going to the parabolics, and the parabolics will be very, very, very short, is that these estimates, then they go up to the maximal regularity of the P-Laplacian equation. This is something that Eduardo Teixeira, who is probably looking at this streaming now, gave contributions to in some recent interesting papers. And okay, what is the maximal regularity of solutions to these operators? And is C1 alpha. In particular, not for every alpha, just for some alpha, let's say a maximal alpha. And in particular, the estimate is the following one. The estimate is the following one. For every alpha, let's say, less than or equal than a maximal alpha, this is still open. The best possible exponent is conjectured to be 1/3, but it's not known. Okay, again with two or more, we prove the following estimate, which tells you that you can control also the oscillations of the gradients in terms of potentials. And this is 1 minus alpha plus 1, p minus 1, p mu xr mu plus w 1p alpha plus 1 p minus 1 over p xr in terms of x minus y to the alpha plus the usual localization term. And this for every alpha where you can get. So now you can also do the same game for the gradient, but of course up to the maximal regularity exponent given by the best possible case at the right-hand side that is 0. Observe, once again, that when alpha goes to 0, now what is this is w 1 over p, which is again this exponent here. Okay, and now we can go to the slides for the last part. I'm going to give you a few sketches of what has been done in the parabolic case. Okay, but these estimates, let's say, they cover in a rather satisfying way the regularity theory for solutions to quasi-linear equations, and they give a formulation in terms of potentials. It is in the homogeneous case. In the non-homogeneous is 1 over p minus 1. Someone conjectures to be 1/3 because they look at solution of the infinity Laplacian equation, which are 1/3. In the homogeneous case. In the non-homogeneous case, by the scaling, you get 1 over p minus 1. Because in some sense, you cancel the degeneracy when the right-hand side is 0, you see. So imagine that you develop the thing, right? And then the right-hand side is 0. You can divide by the gradient, and then therefore is universal. You get the infinite Laplacian. When the right-hand side is non-zero, you cannot divide by du because the right-hand side blows up. And in fact, the fundamental solution of p Laplacian of u equals to 1 is this guy, that exhibits exactly this regularity. Okay, I'm a bit late, so let me take 5 minutes. Okay. Okay, now I'm going to give some results about solutions of these guys. Now, this is very delicate, because there's a very strange interplay. Okay, solutions are known to be in the best possible case in this space, so they are not in LP, so this is the analog of the elliptic theory. We are once again talking about SOLA, solutions obtained by limiting approximations, and everything I'm going to talk about refers to these kinds of solutions. Okay, of course, take P equals to 2, you define the analog of the Riesz potential by using parabolic cylinders with vertex at xt. These are the standard parabolic index. The standard parabolic cylinders, sorry. And they scale as rho in space, rho square in time. This is the vertex. This is like rho. This is like rho squared. Okay, then this estimate follows for the Poisson, for the heat operator. There are plenty of estimates. There are plenty of ways you can derive Duhamel's principle, local estimates, blah, blah. The beef is always the same. Okay, and then you would like to see what happens for general quasi-linear operators and for P larger than 2. For P equals to 2, with, again, in the same paper of Wolf potentials with Frank Dosal, we proved that this holds for any general quasi-linear equation. But this is the case P equals to 2. Now I would like to go to the case P larger than 2, because in the case P larger than 2, there are real differences in the parabolic case. Okay, look here. So the best possible case is when mu is equal to 0. So you have to go to the best possible result. And the best possible result is the following one. And you see that the estimate is anisotropic. It's not homogeneous. You have du here and du to the p minus 1 here. So for p different than 2, this is not homogeneous. You cannot get an homogeneous estimate because, as I told in the first lecture, the equation, the P Laplacian operator, the evolutionary P Laplacian operator, is not homogeneous. This case like p minus 1, this case like 1, and that explains the scaling deficit exponent p minus 1. So the final thing is to have a potential estimate that when mu is equal to 0 reproduces this estimate. Okay, and now the idea is the following one, is the idea that I already explained in the first lecture. You do consider so-called intrinsic cylinders. Intrinsic cylinders are cylinders which are farthly stretched and in the time direction, and they are of this size. So if, in particular, lambda is very large, and we are interested in the case when lambda is very large, then these cylinders are much smaller in time. And on these cylinders, du is like lambda. On these cylinders, du is like lambda. Now, on these cylinders, the equation behaves as this one, and therefore it behaves as the heat operator. So everything looks OK on these cylinders. Therefore, Di Benedetto and Friedman also proved the following result, and this is really the best result that catches up the sharp case. This reproduces the classical homogeneous L1, L infinity estimate of the elliptic case. If on an intrinsic cylinder, this guy is less than or equal than lambda, so if you have a control in average, you have an everywhere control. So a control in LP minus 1 becomes a control in L infinity. And then the homogeneity is perfect, but the price you pay, you have to be on intrinsic cylinders. In fact, once you have this estimate, then this implies the other estimate. So this is the sharpest thing you can go for. This for every lambda.
No relation between lambda and
Here it is.
Yeah,
Lambda controls on the same cylinder. In fact, it doesn't control from below because this is an upper estimate. The relation is here. Lambda is here. It's both on the left and on the right-hand side. OK, and therefore, you define the following intrinsic Riesz potentials. The word intrinsic makes sense just when you relate this to the solution. Up to now, lambda is just a new additional parameter. You take just one lambda. Yeah, and then you define these Riesz potentials. For a fixed lambda, these are equivalent to the other ones. And of course, the interplay is what is important here. And this is the theorem that we have with Tuomo-Cusi that tells you exactly what you expect. If you control both the average of the gradient and the risk potential by lambda, then you get an L infinity control, an L infinity pointwise control. Then you really get it. And this is a very delicate estimate. All in all, you have to develop a lot of new tools, plus revisiting all the others. If you want to prove this, you go for 80 pages proof. You really go for hard stuff. Because essentially, this gives you back all the properties, as we are going to see now, of the P-Laplacian operator in the evolutionary case. Of course, when u is equal to 0, this reduces to the L infinity bound of the Benedetto and Friedman. Okay, how do you test the sharpness of this equation, of this estimate? You want to see, okay, what are these estimates for? They have to replace convolution via fundamental solution. So you want to know if this estimate is good enough to get you back the behavior of the classical fundamental solution. That's the Barenblatt solution. The Barenblatt solution is the solution when the right-hand side is equal to a delta. That's the usual, as you usually compute fundamental solutions. This you get by the original direct computation of Barenblatt. And therefore, the Barenblatt solution decays both at 0 and at infinity in this range. And now it's half a page proof to see that the previous estimate that in turn holds for any general equation gives you exactly this behavior. So the estimate is sharp in this respect, and moreover, it gives you back that the same asymptotic behavior holds for solutions to all possible general quasi-linear equations, because you do not go for a straightforward computation when you do not have the P-Laplacian operator. So this tells you that the estimate is sharp. And in turn, once you get the intrinsic estimate, you can get the non-intrinsic estimate. So you can abandon intrinsic cylinders, and you go for general parabolic cylinders, and you get this estimate. That in turn reduces to the one of the Benedetto and Friedman when mu is equal to 0. So this recatches up everything. Once you have these estimates, then you can go for global estimates via potentials, and then you see that surprisingly enough, you have exactly the same. This estimate here, you see, is independent of P. So no difference at all now, even in the power, between heat equation and P-Laplacian equation. And if mu, okay, you have to have certain integrability conditions at infinity. Then tells you that you can, otherwise other terms appear, of course, because otherwise not every solution is 0 when it's 0. You have to have certain integrability solutions. I mean, okay, and then you have the following theorem. If the risk potential, the classical standard risk potential, goes to 0 uniformly, then you get that the gradient is continuous. In particular, you can go back to the classical theorems, telling you that if you have enough density on the measure, then you get that du is C0 alpha. This was known in the elliptic case, not in the parabolic one. So you get all possible kinds of corollaries now. Now it's a matter of, this you really need a proof. For the first theorem you need a proof, but the second one is just a corollary. Then you get also in this case a nonlinear parabolic Stein's theorem. If the right-hand side belongs to the Lorentz space Ln1, then the gradient is continuous. And this is the borderline case of a result of Di Benedetto, who prescribed that mu was belonging to Ln plus epsilon. Now you go for the borderline result. And And I think, okay, that's all because we are running out of time, but the last part was just a more technical part on a specific theorem. I don't think it's worth reporting now. And this is really the last thing I wanted to introduce. And I usually finish with a picture of this friend of mine who is here, which is here.